please pause the video and try this problem. I hope that you actually did try the problem on paper. You'll benefit a lot more from watching these videos if you try the problems first. Let's start now by numbering all the carbons, including this one. Now, let's identify the roles that atoms will play. We identify this neutral bromine as our leaving group. So then carbon 2 is our alpha carbon because it's attached to the leaving group, and we notice that carbon 2 is a secondary alpha carbon because it's attached to two carbon chains, carbon 1 and carbon 3. Now we can identify this neutral oxygen as a nucleophile or base. Usually we look first for something with a negative formal charge to be a nucleophile or a base as an electron donor, but none of these molecules has a negative formal charge. So instead we identify this neutral oxygen as the nucleophile or the base because it has a lone pair, which makes it want to donate electrons. So which is it? Will the oxygen act as a nucleophile or a base for this problem? Well, the problem told us to draw an elimination mechanism. Elimination means E2 or E1, and E2 and E1 use bases, not nucleophiles. So we know that for this problem, we will be using the neutral oxygen as a base. So we know that we will be carrying out an E2 or E1 mechanism on this problem, but which one? We use the table to decide whether this should be an E2 or an E1 mechanism. We have a secondary alpha carbon. Secondary alpha carbon puts us in the middle row of the table. And our base is neutral oxygen. Neutral oxygen puts us in the left-hand column of the table. Here we're using the neutral oxygen in an alcohol. You should recognize that this molecule is an alcohol. An alcohol is an OH group connected to a carbon chain. So the table predicts SN1 major, E1 minor. But again, the problem told us to draw the elimination mechanism. Therefore, we know that for this problem, we're supposed to draw the minor E1 mechanism. Make sure you write down the name of the mechanism that you're drawing, E1. Now we draw the electron pushing arrows for the mechanism. We're doing an E1 mechanism. In the first step of an E1 mechanism, the leaving group leaves the alpha carbon. So let's draw the arrow for that. The leaving group receives electrons to leave an atom. Now we can draw the product of this step based on the electron pushing arrow. Any electron pushing arrow tells you to erase a bond, or draw a bond, or both. This is an arrow that tells us to erase the bond between carbon 2 and the bromine. The tail of this arrow is on a bond, so this is an arrow that tells us to break a bond. So here I've shown that I've broken the bond between the bromine and carbon 2. Carbon 2 is losing electrons at the beginning of this arrow, so carbon 2 should become one step less negative, one step more positive. Carbon 2 ends up with a positive formal charge, and the bromine gains electrons at the end of the arrow. The bromine starts neutral and gains electrons, so it ends up with a negative formal charge. So here we used these rules for changing the formal charges. The most common mistake would be forgetting to change the formal charge on carbon 2 at the beginning of the arrow. Now we're ready for step 2 of the E1 mechanism. We have to show the base taking the beta hydrogen. So first of all, we have to identify the beta carbon. Remember, we're going to continue to label carbon 2 as the alpha carbon because it has the positive formal charge. And we will label carbon 3 and carbon 1 as our beta carbons because they're attached to the alpha carbon. Now, in this case, carbon 1 and carbon 3 have different connectivity, so they will give us different products. The problem told us to draw the product parenthesis S, which means draw the product or products. So it looks like in this case we're going to have to draw two products. We'll have to show the product that we get when we use carbon 1 as the beta carbon, and we'll also have to draw the product that we get when we use carbon 3 as the beta carbon. I'm going to start by using carbon 3 as the beta carbon. So in this picture, I'll erase this beta label to show that right now I'm focusing on the carbon 3 beta carbon. We need to draw in its hidden hydrogen. Here's the arrow that shows our base taking the beta hydrogen. The arrow shows that the base is donating electrons in order to take this proton. That's why the base goes at the beginning of the arrow, to show that it's donating electrons. We know that the alcohol is a weak base because of our table. Our table tells us that water and alcohols are both weak bases. And we know that this beta carbon is a strong acid because we've learned that in a carbocation, the beta carbon is strongly acidic. This acid-base step makes sense because a strong acid is reactive enough to react even with a weak base. We also need to draw the arrow that shows the pi bond forming between alpha and beta carbons. So remember that when the hydrogen forms a new bond to this oxygen, that's going to free up the electrons in this bond. And we're going to use the electrons in that bond to form a pi bond between our alpha and beta carbons. Remember, to show that we're making a pi bond, the head of the arrow should be between carbon 2 and carbon 3. Do not draw the head of the arrow pointing directly to carbon 2. That would not show the creation of a pi bond. The head of the arrow goes between carbon 2 and carbon 3 to show creation of a pi bond between the alpha and beta carbons. Now, we use these electron-pushing arrows to draw the product from this step. Every arrow tells us to erase a bond, draw a bond, or both. Well, this is an arrow that tells us to draw a new bond between the oxygen and this hydrogen. I show that we've formed a new covalent bond between the oxygen and the hydrogen just by changing this from OH to OH2. So here we used this rule to see that we need to form a new sigma bond. This is a little bit of a complicated rule, but notice that the head of this arrow is pointing to the hydrogen, and the tail of the arrow is on this lone pair. Notice that in this picture, the hydrogen is not yet sharing the electrons in the lone pair. So this is a case where the arrowhead is pointing to an atom which is not already sharing the electrons at the tail of the arrow. That's the type of arrow that tells us to form a sigma bond. This rule is a little bit complicated, so I'm going to go into more detail later in this video to make sure that you understand this rule. But for the time being, I think it's fairly intuitive that this is an arrow that tells us to form a bond between the oxygen and this hydrogen. Now the oxygen is losing electrons at the beginning of the chain of arrows. The oxygen started neutral and it lost electrons, so it should become one step less negative, one step more positive. So the oxygen ends up with a positive formal charge using this rule. The most common student mistake is forgetting to change the formal charge on the atom at the beginning of the chain of arrows. Make sure you remember to change the formal charge on that oxygen. Now we repeat that process for the second arrow. This is an arrow that tells us both to erase a bond and to draw a new bond. The arrow tells us to erase the bond between the hydrogen and carbon 3 and to draw a new pi bond between carbon 2 and carbon 3. I suppose that we already assumed I was breaking the bond between the hydrogen and carbon 3 when I moved the hydrogen to this position, and here I've shown that we've drawn the new pi bond between carbon 2 and carbon 3. So we used these two rules. This arrow tells us to break a bond because the tail of the arrow is on a bond. And this arrow tells us to form a new pi bond because the head of the arrow is pointing to a bond. Carbon 2 is gaining electrons at the end of the series of arrows. Carbon 2 started positive and gained electrons, so it becomes one step more negative, one step less positive. So carbon 2 changes from positive to neutral. Well, now we've finished the mechanism involving this beta carbon. But remember, there's also another beta carbon 1, which we expect to give us a different product. So now we have to draw the mechanism again using carbon 1 as our beta carbon. Now, the first step of the mechanism will be exactly the same as we've already written down. So to save time, I don't need to redraw this first step. Instead, I can just draw things like this. I can put a branch in the mechanism at this point so that I don't need to redraw the first step. And now we can continue now with this step, continue the E1 mechanism. The first step of E1, where the leaving group leaves the alpha carbon, is exactly the same in both versions. So I just reuse this step. Now we're ready for step 2. Now I'm going to use a different beta carbon. Now instead of using beta carbon 3, I've now labeled that I'm going to use beta carbon 1. And again, I have to draw the arrows to show the base taking the beta hydrogen. Here's our arrow to show the base donating electrons to take the beta hydrogen. Now we draw the arrow to show the pi bond forming between the alpha and the beta carbons. We take these electrons that are being freed up and move them to this position to form the pi bond between alpha and beta carbons. So in this version of the mechanism, oops, I numbered this incorrectly. This should be numbered as carbon 1. So in this version of the mechanism, we're using carbon 1 as the beta carbon now, rather than carbon 3. So now we're using carbon 1 as our acidic atom, rather than carbon 3. Now we can draw the products based on these arrows. This arrow tells us to draw a new bond between the oxygen and this hydrogen. So here's an oxygen with a bond to an extra hydrogen. Because the oxygen started neutral and lost electrons, the oxygen changes its charge to positive. This arrow tells us to break the bond between the hydrogen and carbon 1. We've really kind of already assumed that when we put the hydrogen over here. And this arrow also tells us to form a new bond, a new pi bond, between carbon 1 and carbon 2. Here's our new pi bond between carbon 1 and carbon 2. Carbon 2 started positive and gained electrons, so the charge on carbon 2 changes from positive to neutral. And now we've completed the mechanism for this second beta carbon. Oh, I noticed that I forgot to number consistently here. I was going to number this carbon as carbon 6. It really is best to number all the carbons in all of your pictures consistently to avoid mistakes. So let's fix that. Oh, another oversight. I should have written a Br minus that was produced in the as one of the products from the first step here. Let's summarize how we would describe the starting material and intermediate and product here. What type of functional group do we start with in the starting material? Remember, this is called an alkyl halide. An alkyl group, a carbon chain connected to the bromine halogen. So this starting material is referred to as an alkyl halide, and we've already discussed that this starting material is referred to as an alcohol. You need to know that an alcohol is an OH group connected to a carbon chain. Here we have a molecule with an OH group connected to a one-carbon carbon chain. So this is an alcohol. Alcohols are a starting material for many E1 reactions. Now remember, this is called the carbocation intermediate. It's an intermediate with a positive carbon. And do you remember what these products are called? The products are called alkenes because they have carbon-carbon double bonds. So this all matches the pattern that we expect for an E1 mechanism. Remember that both E2 and E1 mechanisms are elimination mechanisms. Now, why are they called that? What is an elimination mechanism? An elimination mechanism is defined as a mechanism in which one or more groups is eliminated from a molecule and no groups are added. So do you see how E1 fits that definition? Do you see that in E1, two groups are eliminated and no groups are added? The two groups that are eliminated are the leaving group and the beta hydrogen. The two groups that were eliminated from this molecule are the leaving group and the beta hydrogen. and no groups were added to the molecule. So this is an elimination mechanism because 2 groups are eliminated from this molecule and no groups are added to the molecule. While drawing this mechanism, we followed these E1 guidelines. We labeled the alpha carbon in all of our pictures. In this picture, we labeled carbon 3 as the beta carbon because that was the beta carbon we were using in this mechanism. And in this picture, we labeled carbon 1 as the beta carbon because that's the beta carbon that we're using in this mechanism. This guideline is particularly useful for beginning OChem students. Beginning OChem students make a lot fewer mistakes if you're careful to always label the alpha and beta carbons that you're using in each E1 mechanism. Clearly, both the beta carbons that we used were attached to 1 or more hydrogens. And we could see from the beginning that these 2 beta carbons would result in different E1 products because the 2 beta carbons have different connectivity. Remember that the connectivity describes the complete series of all the atoms that an atom is connected to and all the atoms that those atoms are connected to. Well, here it's very easy to see that the connectivity of carbon 1 is different from the connectivity of carbon 3. If you were going to describe the connectivity of carbon 1, one of the things you would start by saying is that carbon 1 is connected to 3 hydrogens, 3 hidden hydrogens. Well, clearly carbon 3 is only connected to 1 hydrogen. That's enough by itself to see that those 2 beta carbons have different connectivity, so we can trust that they will result in different E1 products. And you should be able to compare these 2 products and see that they clearly are different molecules. Now, here is a checklist of things to do for reactions in general, not just for E1 reactions. Number all the carbons in the starting materials, intermediates, and products, and make your numbers consistent. So I numbered all of these carbons in the starting material, and then I tried to number all the intermediates and products consistently with the numbers I chose at the beginning. Why are we using these numbers? Well, one of the most common student mistakes is accidentally adding or dropping carbons in your intermediates and products. And if you number all the carbons consistently, that makes you much less likely to accidentally add or drop carbons to your pictures. So notice that these numbers we're writing down are for our own personal use. They're not official IUPAC naming numbers. So you can write down any numbers you like as long as they're consistent. You don't have to follow IUPAC naming rules. I know it might seem tedious, but my experience is that students almost always start accidentally adding or dropping carbons if they're not careful to consistently number all the carbons in all of their pictures. So this is important advice for a beginning OChem student. Notice how we're labeling the roles that atoms will play in each step. Here's the leaving group in the first step. Here's the weak base and strong acid in this step. I encourage you as a beginner to label the roles that the atoms are playing and identify the clues that tell you that the atoms will play the roles. We know the bromine will be a leaving group because we've memorized that neutral bromine is a good leaving group. We know this oxygen is a weak base because we've memorized that neutral oxygen is a weak base. It's the lone pair that makes it basic. And we know that this is, the beta carbon here is a strong acid because we've learned that in a carbocation intermediate, the beta carbon is strongly acidic. Again, it might seem tedious to have to go through this each time, but it's really crucial that you master the use of these roles in OChem reactions. And the more you practice applying the roles each time, the faster you will gain skill with the roles. So I encourage you to actually label the roles that atoms are playing in each step, just as I am demonstrating in the videos. We've talked about labeling the alpha and also the beta carbons for E1 and E2. Write down whether the alpha carbon is primary, secondary, or tertiary, like I did here. You need to write that down because this is crucial information for using the table to determine the mechanism. Use the table to determine the mechanism and write down the name of the mechanism. It's crucial to write down the name of the mechanism because very commonly students determine that the mechanism is E1 and then they forget and accidentally draw a different mechanism. So to make sure you don't forget which mechanism you're trying to draw, write it down. Don't begin drawing the products for a mechanism step until you've finished drawing the electron pushing arrows for that step. So for example, first draw this arrow before you draw this intermediate. And then again, first draw both this arrow and this arrow before you try drawing this product. First draw both this arrow and this arrow before you draw this product. We've been showing that the electron pushing arrows are the tools that we use to determine the correct way to draw the product. But you can't use that tool unless you've finished drawing the arrows for the step before you draw the product. Don't just draw the product that you guess you're going to get or that you expect to get. Instead, draw the electron pushing arrows and then draw the products that the arrows tell you to draw. That's the way to improve your skills as a beginning OChem student. And you can check that you're done when your main product has no formal charge. Here we ended up with these two main products with no formal charge, and that was the clue that we were done with our mechanism. SN2 mechanisms, unfortunately, are an exception to that rule. I talked about that in the SN2 series. Know that if you try to follow all the items in this checklist, it might seem tedious and seem like it's slowing you down. But my experience is that beginning students make the fewest mistakes and develop their OChem insight and skills the most quickly if they make an effort to follow these steps for each mechanism, and I'll be demonstrating those steps in the problems we try in these videos. As you develop OChem mastery for each topic, it will become less important to follow all of these steps. But right now, as a beginner in OChem and a beginner in this topic, these are good steps to follow. Now, I mentioned that the electron pushing arrows tell you how to draw the products. Here are some of the rules that you use to draw the products based on the electron pushing arrows. So I want to talk in a little bit more detail about this particular rule, which is a little bit more complicated than the other rules. Let's make sure we understand when an arrow tells us to form a sigma bond. Form a sigma bond when the arrowhead is pointing to an atom which was not already sharing the electrons at the tail. I know that's a little bit complicated, but here's what I mean by that. Take a look at this arrow. So notice that the head of this arrow is on the hydrogen, and the tail of the arrow is on this oxygen. So the tail of this arrow is on this lone pair, on the oxygen. Well, notice that in this picture, the hydrogen is not yet sharing the electrons at the tail of the arrow. Right now, the hydrogen has no possession at all of this pair of electrons on the oxygen. So this is a situation where the atom at the head of the arrow, the hydrogen, is not already sharing the electrons at the tail, the lone pair on this oxygen. So this arrow meets this qualification. So this is an arrow that told us to form a sigma bond. So you can compare that with this arrow. Take a look at this arrow. Notice that in this case, the head of the arrow is on the bromine, and the tail of the arrow is on this covalent bond. Remember that the covalent bond represents a pair of electrons in the bond. Well, do you see that in this picture, the bromine at the head of the arrow is already sharing the electrons at the tail. Even in this picture at the beginning of the step, the bromine is already sharing the electrons at the tail of the arrow because it's already sharing the electrons in this covalent bond. So this arrow does not meet this qualification, and therefore this is an arrow that does not tell us to form a sigma bond. When the arrowhead is pointing to an atom which was already sharing the electrons at the tail of the arrow does not tell you to form a bond. This arrowhead is pointing to the bromine, which is already sharing the electrons in the covalent bond at the tail of the arrow. So this is an arrow that does not tell us to form a bond. Instead, as we've seen, this is an arrow that told us to break a bond. When the arrowhead is pointing to an atom which was not already sharing the electrons at the tail, that's when the arrow tells you to form a sigma bond. So this arrowhead is pointing to the hydrogen, and in this picture, the hydrogen is not yet sharing the electrons in the lone pair at the tail of the arrow. So this is the type of arrow that does tell us to form a sigma bond. I hope that that explanation clarifies this rule. But I also think that with time, you just get an intuitive feel that this arrow tells us to form a new bond. Remember that every arrow tells you either to erase a bond or draw a bond or both. And I think it's pretty intuitive that this arrow is not telling us to erase a bond. Therefore, it must be telling us to form a bond. I took the time to explain this because it's important for you to understand that there are rules for using the electron pushing arrows. And if you follow those rules, they give you a reliable way to correctly draw the products. So like I said, you're not supposed to have to guess what these products look like, or memorize what the products look like, or just draw what you expect to get. If you follow the rules, such as these rules, then the arrow should tell you the correct way to draw the products for each mechanism step. Here again is the summary of the rules for using the electron pushing arrows to draw the correct products from the mechanism step. Every arrow tells you to erase a bond, or draw a bond, or both, following these rules, and also make sure that you always change two formal charges at the beginning and at the end of the chain of arrows. The most common mistake is forgetting to change the formal charge at the beginning of the chain of arrows. By the way, I should mention, do not change the formal charge for any atom in the middle of the series of arrows. For example, for this step, the oxygen was at the beginning of the series of arrows, so we changed its charge from neutral to positive. This hydrogen is in the middle of the series of arrows, so we did not change the formal charge on this hydrogen. The hydrogen started neutral, and the hydrogen stayed neutral. Also, carbon-3 is in the middle of the series of arrows, so we did not change the formal charge on carbon-3. Carbon-3 started neutral and stayed neutral. On the other hand, carbon-2 is gaining electrons from the end of the series of arrows. So we did change the formal charge on carbon-2 from positive to neutral. For every mechanism step, you change two formal charges, at the beginning of the chain of arrows and at the end of the chain of arrows. Don't change the formal charges for atoms in the middle of the series of arrows. And again, the most common mistake is forgetting to change the formal charge at the beginning of the chain of arrows. So try to watch out for that. Here's another point. Notice that in the second step, we used the alcohol as the base rather than using the bromine, even though the bromine was negative, which you might think would make it want to donate electrons as a base. Well, we talked about this issue in the previous video. It turns out that Cl-, Br-, and I- are very weak bases. And therefore, when water or alcohol is the solvent, it's generally better to use the water or alcohol as the base rather than Cl-, Br-, or I-. Well, here we have alcohol. The alcohol is the solvent. When you see alcohol in the starting materials, we generally assume that's also being used as the solvent. So it's preferable to use the alcohol as our base rather than the Br-. This is the approach that most professors prefer. This mark doesn't belong there. Let's erase that. In the next video in this series, we will try a more complicated problem that involves an E1 mechanism. Did you find this video to be helpful? If so, you can support the videos by making a monthly pledge at my Patreon page. You can visit my Patreon page by clicking the link on the screen, or by using the link in the video description box. Thank you.